I'd like to talk to you about the quantum mechanical model. So in the last video, I taught you guys a little bit about Max Planck, and you heard me say particle wave duality, where waves, like energy, can behave as particles. Well, if waves can act like particles, then particles can have wave-like functions. All right, so that's the idea here, that particles, like electrons, can have wave-like properties. So what I have here is a schematic of a topic taught in AP Physics. These are the harmonics, okay? So harmonics, basically to give you an idea, if I take a rope and I attach it to a doorknob and I begin to propagate waves, those waves are going to propagate through the medium, okay? Through the rope. They're going to hit the door and reflect, all right? If I get just the right frequency and the right length of rope, I can create what are called standing waves. And standing waves have very discrete and exact intervals. Does that sound familiar? Here we have the fundamental harmonic. Here we have the second harmonic. Here we have the third harmonic. Here's the fourth harmonic. N equals 1, N equals 2. Does this sound familiar? I hope so. Okay, so these exact patterns of standing waves occur when waves reflect and constructively and destructively interfere in such a way that they create these standing discrete waves. So you can see in this animation here how this kind of works. Now the length of the string is the same for all of these, but the frequency is varying, and as a result, when the wave reflects just the exact frequency and length of string, you get these very discrete areas. All right, so electron distributions as standing waves gives the existence, leads to quantum numbers. I'm going to talk to you about that in the next video, okay? These quantum numbers are a set of numbers that describe not only the size and shape, but the orientation in space of electrons. Okay, and they give an almost like an address, an exact set where no two can share the same 4 quantum numbers. I'm also going to begin using the Cartesian plane in 3 dimensions, X, Y, and Z, because this is a 3-dimensional phenomena for where electrons, these particles that are acting as waves, exist. So, what is an orbital now? Am I blowing your mind? Well, an orbital is actually a mathematically derived space. It's a region in space, and it's based on a very complex set of equations and mathematical relationships dealing with wave functions. All right? Now, these equations, like the Schroeder equations, are able to predict with different probabilities where electrons reside. Okay? Very, very cool and makes your mind hurt. So an atomic orbital is now defined as a region in space within an atom that encloses where an electron is likely to be found 90% of the time. It is a 90% probability distribution for where electrons are located. All right, so you'll see in this schematic here, and don't worry about 1s, 2s, 3s, I'll get to that in the next video. You'll see that the areas are labeled as nodes. That may sound very familiar. I just got done talking about the harmonics, and the harmonics are made up of nodes and antinodes, okay? So here in this one, we see there are 2 nodes, okay? Now, a node for a wave is an area of complete destructive interference where the waves will completely cancel out, equaling 0. Well, a node in the orbitals is a region where there is 0 probability of an electron residing. So again, particle wave duality. This is incredible stuff. An electron's angular position relative to the Cartesian plane, remember we're in 3 dimensions, is going to change the probability density and thus the shape. Okay? So this is when I want you to look at the 4 different shapes or orbitals. We have the S, P, D, and F. Okay? Now, this S is shaped like a sphere. So if you imagine the sphere, no matter how you turn it, it's going to have this sort of spherical shape because its angular position relative to the Cartesian plane is not changing. But if you look at P, D, and F and imagine deviating at different angles in this plane, it's going to result in a different shape. Okay? And so you can see the shapes here. P's is like a almost like a dumbbell. D's are like clovers. F's it gets even crazier. But look at this. Look at this. Go back and start thinking about quantum theory. Think about the Bohr model. Think about atomic spectrum. Think about quantized energy levels. Think about electrons absorbing energy, jumping and falling. But the jumping and falling occurs between very discrete units. Now, apply that to a more complex model based on mathematics, based on a 90% distribution probability. And you can sort of make that comparison here when you look at this. Go back and think about those Rutherford, those electrons perfectly orbiting in circles, which could never happen because they would lose energy. They would essentially spiral into the nucleus, all right? But here, with these particles acting as waves, it's almost like they're teleporting, but that's not what they're doing. Okay? All right. So orbitals SP, D, and F are corresponding to these specific regions. All right? So I want you to get out your periodic table or print another one from pedersenscience.com or wait until tomorrow in class and I'll give you one, but I want you somehow to denote, make some designations on your periodic table here. Now, there is a little mistake here, and I thought I had that fixed, so let me see if I can do that real quick here. This here, and I did have it fixed, but that's okay. That should be blue. Okay, so helium should be blue. All right, so SP, D, and F, this is where they are on the periodic table. So we typically will call these the S block, the P block, the D block, and then the lanthanides and actinides, the F block. Okay, all right, so what that means is they have these corresponding orbitals, which again is a probability distribution for where an electron will be located. So you notice in the P here, you know, in the S, we just have this one spherical shape, but when we get into P, all of a sudden we have an X, a Y, and a Z. And then same with D, and F gets just crazy. All right. So this is where these electrons are located, and they are moving as quanta. All right. As particles exhibiting wave-like functions. You want to see what they all look like? Take a look at this. This is really cool. Look at the F block down there, the green and white at the bottom. These are some bizarre shapes. These are the orbitals based on the mathematics. So just maybe at this point, this bizarre animation that I showed you 2 videos ago doesn't look so crazy after all, because this is what electrons are really doing. They are exhibiting particle wave duality. They are moving in discrete units of energy, giving these distribution probabilities. This video has led up to and now gone through the quantum mechanical model of the atom. This is the current model of the atom. And it also begins to get into light, something I'm going to talk even more about in upcoming podcasts, including the electron configuration for atoms and ions. I will see you guys in class.